Okay, today we're going to talk about phase equilibria, and in particular we're going to emphasize the so-called K values that are used in calculating phase equilibria. And to begin with, I just want to start by stating what I mean by this phase equilibrium issue. Basically, we're talking about having some volume, some point in the system, reservoir and the production pipe going to the surface, or at the surface, gathering pipelines, maybe at the separator. Basically, at some point in the system, having a known pressure and temperature of that particular point, and wanting to identify whether we have oil and or gas for a given. In addition to having the known pressure and temperature, we're going to assume that we also know the overall mixture composition at that point, the molar amount of methane, ethane, and CO2 and so forth. That composition is known, as well as the pressure and temperature. And then the question is how much oil, how much gas in terms of moles, mass, and volume exist. What is the composition? So, for example, the moles of oil, the moles of gas, and the molar composition of the gas and the molar composition of the oil. Where I think yesterday we defined this molar composition as how many moles of component I in that gas phase divided by the total number of moles. And we're going to assume that we have a total number of moles N, which is the sum of Ng and NO. And the oil composition is the sum of the moles that are in the oil phase divided by the total oil phase moles. For right now, we're going to ignore water as a phase. We might very well have, and often will have, water in the system. It will generally be contacting both the gas and the oil. I'll just put kind of in with dashed lines that we might have water in the system. We typically don't do three-phase calculations, including water, for some reasons we'll talk about next hour. So for right now, we're just going to talk about gas, oil, phase equilibrium. So what we know at some point in the reservoir, in the production pipe, maybe at the surface gathering pipes, gathering lines, and ultimately at some separator unit. I'll just kind of sketch it. We've got our reservoir here. We've got a well drilled through the reservoir. Of course, this is not a proportion. This is the, for example, the well, and then we've got maybe gathering line on the surface, and then finally it reaches a separator where the mixtures split into an oil stream and a gas stream, maybe further processing or transportation. We've got our reservoir, our production tubing, as we usually call production pipe, is production tubing, and maybe the gathering system, G for gathering system, and then this is our separator. And if we take at any point in the system, down in the reservoir, of course, we have reservoir temperature. The temperature is decreasing as it flows through the tubing and the gathering line usually, and then so we have a changing temperature, and certainly the pressure will be dropping as the reservoir fluid flows into and reaches the separator. So we're interested in knowing at each point in the system, basically if we have gas or oil, and if we have gas or oil, how much of the two phases, and what are the component partitioning into the two phases, the compositions. So this is referred to as molar compositions of the phases, as well as the overall total molar composition. Any questions about this setup? So this is the problem we're going to be talking about. Now, next week we're actually going to do the methods of calculation. We're going to talk about how to solve the calculation problem to determine the number of moles of gas, the number of moles of oil, and their compositions. But today we're just going to discuss the main method, kind of the main information needed to make those calculations. Okay? And in particular, something that's referred to as K values, written as Ki. And those equilibrium ratios, they're sometimes referred to Ki, where they're defined as the ratio of mole fractions of the component I in the gas phase, the equilibrium gas phase, divided by the mole fraction of the component in the equilibrium oil phase. And remember, we talked yesterday, if you have two phases together, then we know the two phases each are saturated. It's a saturated oil and a saturated gas, and that's distinguishing, so we can actually well define the phases. So this is the definition of the K value, and we're going to study and talk about today the dependence of these K values on pressure, on temperature, and on the overall composition, which I'm going to write. Usually I write the overall composition Zi. But because I'm now talking about the K value of one particular component, K, of I, it's not dependent only on the mole fraction of that component, it's dependent on the mole fraction of all of the components, the total composition. So I'm just going to write that as Z, or I might break down in like a vector. Okay, it's a string of components. So the methane K value depends not only the methane mole fraction total, also on the ethane and the propane and the CO2 mole fraction as well. All right? So this is the total composition. And that's mainly what we're going to talk about today, that dependence. Once we understand that, basically how they depend on pressure, temperature, and composition, and why they depend in a certain way on pressure, temperature, and composition, then the actual computation of this two-phase calculation will, I think, have more meaning. It's just pure mathematics, the solving. Here we're trying to understand a little bit the physics of what's going on. Okay? So that's the game plan. Now, from the point here in the well bore, this is referred to as the well bore, the composition that is flowing in at the well bore will be the same composition here and here and here and entering the separator. Okay? That will be a composition that doesn't really change. Okay? What's going in is going out, averaged over some time period. So those are the same compositions. Now, if you look at the composition out here in the reservoir, which is flowing into the well bore, this composition might be changing as it's flowing in towards the well bore. If it goes from being single phase into being two phase, Maybe the one phase has more mobility than the other phase. The one phase lags behind. The other phase moves forward more quickly. So the composition of what we'll call the in situ reservoir composition, it may be equal to, but it may not be equal to what we call the wellbore. And because the wellbore composition is the same as what we call at this point here, this point that enters the separator, this is called typically the well stream composition. I know there's a lot of terms, a lot of words, but we have to get them out of the way. So this well stream is kind of what enters, it comes out of the well at the surface. And that is the same as the composition that enters the wellbore. So this well stream composition, which basically is the same as the wellbore composition, okay, that in situ may be the same or it may be different. Okay? But the point is that we're now going to say, and certainly next week when we do the calculations, that wherever we are, we know that composition. Okay? And now we're interested in how that composition partitions into phases and how the individual components partition into the two phases. All right? So now is the behavior of the so-called K values. The first thing is that these K values basically represent in lay terms. In other words, you talk to your mom and dad, not Finhaven, his dad knows a little too much to be talking about him as lay terms, but you talk to your cousins about what you're doing, and what they represent this is a quantity that gives a relative preference of that component to be in the gas phase or the oil phase. It's not an on-off switch, okay? But it's a relative tendency. Does it prefer going to the gas phase as opposed to going to the oil phase? Okay? So it represents, in lay terms, the relative preference of component I to be or move to in the gas phase or oil phase. Okay? And basically, if it's the gas phase we're talking, if it has a relative preference to be in the gas phase, then the K value will be greater than 1. Okay? Greater than 1. And if it has a relative preference to be in the oil phase, it will have a K value less than 1. Okay? Now, that's the general comment about the K values. Now, a second general comment, lay comment, is that we can make more money I say we, okay? Generally, you're not going to be owning the things unless you're some tycoon that becomes an oil and gas producer. Your company is going to make more money, the industry is going to make more money by selling component I okay, propane, butane, pentane, okay, these components, as part of the liquid. And I would say not just the liquid phase, but the ultimate, you know, at the end of all processing, the ultimate processed surface liquid phase. If we can keep that component in the liquid as it is processed down to this ultimate surface phase. In other words, we're going to do stuff with these streams that ultimately leads to a stock tank barrel. Okay? Selling today at $116 per barrel, per stock tank barrel. Okay? If we can keep the component as part of that liquid phase, then we're going to make a lot more money, somewhere between 5 and 10 times as much for every molecule of component you can keep in that phase than if it ends up in the gas phase, being sold or burned or given away. All right? So now from the reservoir until the entry to the separator, we don't really have much control over the composition. We might have a little bit of control in the reservoir in some situations, but basically once it hits the wellbore until it reaches the separator, it's just the composition the reservoir is giving up. We don't have any control. We can change the pressure and temperature as we like from the wellbore to the entry of the separator. Nothing's going to change the composition. Nothing's going to change the K values that make any difference. But what we can control basically is all of this surface process, which I'll refer to as capital P, and we'll talk some about that in the second hour, is in that surface processing we can control in pressure and temperature. Maybe, okay? And we try to do that to keep as many of the components as possible in the ultimate stock tank oil. Now generally that's not our job as petroleum engineers. It's the chemical engineering, process engineering job. Okay, but that's what they're doing. And they basically do that to try to keep as many of the components with as high or low K value as possible. You want a high or low K value to keep that component in the oil phase. You want it as low as possible. Okay? That's the deal. And it's generally somewhere between 5 and 10 times the value than if the component is sold as part of the gas phase. It depends on the gas price. Yeah.
You say that if you're able to change some conditions in the pipeline, in the well, in the reservoir, to the waste stream,
Yeah.
you still get the same K values.
Well, no, you get different K values. You get different K values. If you're changing conditions in here, in this transport, okay, it changes the K values, and locally it changes the amount of the component being the gas and the oil. But no matter what you have in the way of pressure temperature profile to the point here, it's only after you start separating out the phases and doing all of this processing will it actually make a difference. Okay. So these are maybe the two main things to remember. At least you can talk about when you go home. Talk about this with your folks. So now what we're going to do is I'm going to plot up a sketch of how the K value varies with pressure. Okay. And I'm going to use units of bar, which is most familiar to you guys, absolute. 1, 10, 100, 1,000 bar. And PSI, this would be, I'll just make it in gray, 15 PSI, 150 PSI, 1,500 PSI, and 15,000 PSI. This covers pretty much the range of two-phase conditions in petroleum systems. And then we're going to plot, and that's obviously a log scale, as I've drawn it, and we're going to have K values also plotted on a log scale, 0.1, 0.01, and 0.001, and 0001. And then we got 10, 100, and so forth. So it's a log scale. And processing conditions, I mean, within our petroleum system generally range from 1 to 1,000 bar, I mean, in the extremes. Okay. Now, the first K value I'm going to plot is for a heavier component. Okay? A heavier component. Heptane, decane, dodecane, you know, C20, something like that. And I'm going to draw that, try to draw it more or less correctly. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, it's going to be something like this. And that's going to be CN, where basically N is greater than about, 3 or 4. They'll all look like this. All of the components will look like that. This plot is made for a constant temperature, and we'll look and see what the effective temperature is. Once we understand the pressure dependence, we're going to look at the temperature after that. And then the next component I'm going to plot is methane, which is typically what we would consider a component that likes to be in the gas. And sure enough, it's going to look something like this. It kind of goes off the chart for this figure here. Because that's not a very nice picture. I'm going to try it one more time. One more time. Problem is this. Something like that. That's going to be methane. It'll look similar also. Nitrogen will look like that. C2 will look a little bit like that. Maybe H2S. But both CO2 and H2S could go below 1 and come up again. But typically methane, ethane, and nitrogen will all be monotonically decreasing as you go to higher pressures. Whereas all of these components, these heavier components, C3, C4, and so forth, will typically be non-monotonic is very important, and have a minimum. Okay? And what is minimum? A minimum, in this case, is a good thing or a bad thing? It's a good thing, right? So we're going to try to play a little bit off of that minimum, if we can. Now, unfortunately, it's at a relatively high pressure. Okay? And most of the processing that is done, where we have control of the pressures and temperatures in the process, the surface processing, are typically at conditions of this pressure to about this pressure. This is where we do our surface processing. And here we, in a sense, have control of the pressure and temperature. If we put enough money in, we can change the pressure and temperature to try to keep the components in the liquid phase. And typically out here is where we have reservoir stuff going on, maybe production in the tubing at these higher pressures. They may also be at the lower pressures as well. So this probably should be kind of, this goes all the way. Okay, so this would be reservoir can go, and tubing production can go all the way from here all the way up to here, whereas the processing goes from here basically to here. Okay. Now, the point where there's a couple of things that you should observe. The first thing is that in this low pressure range where we have so-called process, this less than about 100 bar, all of these K values have a characteristic, and that is that the slope of this line is -1. Okay? Is -1. And what that means is that the K value is inversely proportional to pressure. Okay? The lower the pressure, the more that component wants to be in the gas phase, the less money we're making. Okay? The other thing is that for these components Cn, that I call Cn, they'll actually cross through the value of Ki equal to 1. And they do that at a very specific pressure. Okay? Let's go back to yesterday. We looked at water at 100 degrees, a pure compound, at 100 degrees C and 1 atmosphere, right? And we realized that we could have our steam and our liquid, right? Our gas and our liquid. And that shouldn't be S for, that would be like solid. So gas, that's steam, and our coffee, right? But what is the mole fraction? There's only one component. What is the mole fraction of H2O? The moles of H2O component in the total moles of the gas. But there's only H2O, right? Okay, so this must be equal to 1. And what is the mole fraction of H2O in the liquid? It is also 1. So what is the K value of H2O at the vapor pressure for that particular temperature? Okay? It must be equal to 1 over 1. And you can even do this with mom and dad, and you get 1. Okay? So this crosses the 1 line here at the vapor pressure of that particular component at that particular temperature. Okay? So if your temperature that you're looking at is 200 degrees Fahrenheit, for example, okay? 200 degrees Fahrenheit. And if this crosses at about 1 atmosphere, right? Okay? What is the normal boiling point of that component? What is the normal boiling point of that component? Normal means at what temperature does that component boil at normal pressure? That's why it's called normal boiling point. At 1 atmosphere. That's 15 psi. So What is the normal boiling point of this system? If we say this is 200 degrees Fahrenheit, what is the normal boiling point of that particular component I've drawn? Huh? 200 degrees Fahrenheit. Okay? Now, which component that is, I don't know. I mean, I don't know. But we can go and we can look in the book, in the appendix. That's not going to be very efficient, so I'll have to... There we go. And 200 degrees Fahrenheit, you add 460 to it, right? That's 660 Fahrenheit. I'm ranking. 660 normal boiling point somewhere here. 660 right there. Heptane. So the component I drew must be C7. Okay? So it crosses here at the vapor pressure at your particular temperature. So if you know the vapor pressure of any component at that temperature, and that we know for all components at all temperatures, that's an easy thing to come up with from tables and charts and correlations. And we know that the slope is going to be -1, okay, and nothing else. That means we basically know the K value of that component at all pressures. And if I change the temperature to a higher temperature, what will happen to the vapor pressure? If I go to 250 Fahrenheit for normal heptane, what happens? What does the vapor pressure do?
Decreases.
Huh?
Decreases.
Okay, remember our vapor pressure curve looks like that. Temperature, vapor pressure, critical point, and we're at 200 here. And if we go to 250, well, that would be a little bit high. If we go to 250, it's going to increase, okay? That means down here, for this same component, it's just going to go at a higher temperature. Let's make it a different color, purple. This will be at 250 Fahrenheit. And then this C7 component is going to have, without my wiggly hands, it's going to have K value that looks something like this, at least down to approximately 100 bar. So immediately, if I can get the new vapor pressure, I can get the entire set of K values for this range where we have lower pressures. Okay. So in this low pressure range, we have a relatively easy problem of coming up with the K values. For all these different components, all we need to know are their vapor pressure curves. That's all we need to know. And people way, way back were correlating vapor pressure curves of all these components, everything we'll ever see, pretty much, with very simple relationships. Okay? So that we can come up with. If we know a little bit about each component, either its name or something about the component, we can generally come up with the vapor pressure curve for that component. Once you've got that, you've nailed all the K values in this low pressure range. And those K values are the ones that we're going to be trying to manipulate in terms of pressure and temperature to maximize the amount that each component stays in the stock tank oil. So we make the most money. So we get a raise. Yeah? So we keep those high salaries. All right? Any questions? Okay. So all we need basically is if we have the vapor pressure of a given component as a function of temperature, then we automatically have the K value of that component as a function of pressure less than about 100 bar, probably should be a little bit less than that, in any temperature. Okay? And in fact, the equation is equal to vapor pressure over pressure. It's that simple. That's the equation for K value. Now, another thing that's important is to make a note of is that in this pressure range, this low pressure range, is that it doesn't matter if that component, heptane, is together with the troll gas or the Gawar oil in the Saudi Arabia, or the North Field in Qatar, or in the Oklahoma City field, where I grew up, It doesn't matter. Heptane is going to behave like heptane, and it don't matter who's around it. Okay? It's a little bit like ourselves, okay? You give us enough space, maybe I won't tell you all the things I tell, if I'm in the middle of the desert with nobody around, okay? But basically you'll get me behaving the same way if there's you guys or if you fill the whole group. Well, if the whole room is full, I might behave a little differently, but in general, at these conditions, but if you put all the world's presidents and leaders in the same room, the pressure's a little bit higher, yeah? What's Obama going to say? The NSA is after me. So if you fill this with people other than like normal people like yourselves, these abnormal people, the world leaders, there's going to be a higher pressure in the room, and I'm not going to probably behave the same way. Okay? But down in this region, the K value is basically independent of the overall composition. From pure heptane by itself, me in the middle of the Sahara, nobody else out there, to me together with you guys, okay? But if you put the pressure on me, okay, you get all the professors of the NTNU, they're going to evaluate Curtis. We're going to fire this guy, or we're going to let him keep teaching. And you fill the room with all these dignitaries or something. Pressure's on me. I feel higher pressure. Then I'm getting out into this other range where I'm going to behave differently, okay, for whatever reason. And it's this range out here and how this high pressure behavior looks. That's what we're seeing mainly in the reservoir and in some of the production tubing where you have high pressures. Okay? There, heptane behaves differently in the Troll field, in the Qatar North field, in the Oklahoma City field. Okay? Behaves differently in every field. So that's this high pressure range out here. So out in this range, you have a relatively strong dependence on the overall composition. Okay? The way I've drawn it may be here for the Troll field. I don't know. If I take for the North field, maybe it'll look something like that. Methane also is going to change a little bit. That's the North field. If I take Gawar, that's the world's biggest oil field. Maybe it's going to look a little different. Maybe it's going to look like this. Something like that. And for some reason, it's special. Saudi Arabia, it looks like that. Now, to me, this figure looks almost like a nose. And everybody has different noses, the tip of the nose. Okay, the general feature of the nose is going down is fairly common to everybody, but it's basically the shape of the nose is different for every individual, and that's true. But there's some general trends that are the same. So we now know what the general trends are, and we know not everybody has a slope of -1, but okay, generally sloping down. But the tip of the nose is different for everybody, and that's what's beautiful, okay? And that's why I love working with this subject, because every field I come across, the tip of the nose is different. And the challenge is figuring out how to model the tip of the nose And it's not easy. It's complicated. See how nonlinear it is? It's going orders of magnitude in a very small pressure range. There's a lot of stuff going on. There's a lot of interaction amongst the molecules. Heptane becomes very sensitive. I become very sensitive if you fill the room with, I don't know, some kind of species that, that I don't, snakes or something, I don't like. So you get very peculiar behavior in this high pressure range. And to figure out how that is different from field fluid, reservoir fluid to reservoir fluid, that's a cool challenge. And it's difficult to do. Okay? And by the way, the heaviest components, these megamolecules, C30, C100, realize that they're coming down here. Well, they're off the chart. I mean, I'll draw it as far as I can down here. But this is one of these megamolecules. It doesn't start turning the corner till about the same point. And we're now down at 10 to the minus fifth. And it has to go from 10 to the minus fifth to 1, where all of them converge together. You see? You're getting components changing 5, 10, 15 orders of magnitude over a very small pressure range. And you have to get every one of those components to converge up there to 1 at some pressure. Now, which pressure it converges to, that will depend on which nose we're looking at, which reservoir fluid. Okay. Now, if you understand this, then you don't need Gibbs or or all the thermodynamics courses you had before. Your Helmholtz energy, and unless you're going to be a researcher or scientist or something like that, you don't really need to know all these things. But there's a lot of people who do those kinds of things who maybe don't really understand the kind of the layout of the system. Okay, so all I want you guys to carry with you is this fundamental behavior. The partitioning ratio, which says if the component prefers to be in the gas or the liquid, and relatively how much. If it's 10 to the minus 5, it really doesn't like to be in the gas. Okay? I mean, like really, 5 orders of magnitude, not liking to be in the gas. So if you got 1,000 of those molecules, you don't have enough to even put something up in the gas, right? So, and on the low pressure side, it's simple. It's easy. Everybody knows boiling water, so everybody can learn the vapor pressure curve. That's it. So you already know all that low pressure stuff. The only thing you really have to realize is that if you go to a higher pressure, all of the K values will have to converge to 1 at some pressure higher, and somewhere typically less than 1,000 bar. So in 1 order of magnitude of pressure, it's got to turn the corner and come up to 1, all of the components. That means there's a lot of stuff going on there. So the molecules are really starting to interact with each other in different ways, and it's complicated stuff. Okay. Temperature dependence we now know, just from this very simple exercise. Vapor pressure increases with temperature. You then know the whole curve shifts up. So you know pretty much everything you need to know. Any questions?
Does the chart mean that for oil processing, it's like, if you want to have more money, it's essential to have higher pressure, like till this 100 bars, because it would give us opportunity to have these molecules in oil phase. So for oil processing,
To process,
have the processing closer to 100 bars than to 1 bar for like any single oil of the world,
well,
like in general.
yeah, if you had a single separator up here, and that's it, then you'll typically find there's some optimal pressure, because they turn the corner at different pressures. They turn the corner a little bit differently, each component. And you have to sum all of the components, not just one component. And what you want is the largest total amount of oil, which is kind of the addition of all the components. So what you'll find in general is that, yes, there's some optimal separator pressure, first stage, that will give you the most oil. But you can get yet even more oil if you add more stages and you start playing with the pressures and temperatures of each stage. Okay? And you can also try to do extraction of the gas, components out of the gas into the liquid. So there are, that's a whole, there's a whole other group of engineers sitting in another room talking about how to do this kind of thing. But at the end of the day, what you want to do is maximize this total volume by manipulating pressures and temperatures and numbers of stages and how they're connected and so forth. Okay? Any other questions? We'll take a break.